Hello everyone, this is Aparna Shetty, Assistant Professor, Department of CSE, AJ Institute of Engineering and Technology. So in this video lecture, I would like to continue with Module 3, that is Association Analysis, from the subject Data Mining and Warehousing. So in this video lecture, I will be covering the topics objective measures, interest factor, correlation analysis, IS measure, different properties of the objective measures, alternative measures of interestingness, and finally Simpson's paradox. So this would be the end of your third module. So let us begin this lecture. So interest factor. Now the T confidence rules shows that the high confidence rules can sometimes be misleading because the confidence measure ignores the support of item set in the rule confidence. Okay, now we have already seen this T confidence rules, yes or no. In the previous example we have calculated the tea coffee example. In that we have calculated the confidence, and it is a high confidence rule and it would be sometimes misleading. The reason for that is because the confidence measure ignores the support of the item set in the rule consequent. Now what is the rule consequent? Okay, suppose now if I have a rule, say A implies B. Okay, now how is the confidence calculated for the rule A implies B? Support of both the items, item set A union B, right? Support of A union B divided by support of A. Okay, this is how we are calculating the confidence. Now over here in this rule, the left hand side of the implication is called as antecedent. This is called as antecedent. And the right hand side of this rule is called as a rule consequent. So this is called as a rule consequent. Now here if we see, when we are calculating the confidence, we are including just the support of A. That is, support of just the antecedent of the rule is considered, whereas the consequent support is not considered. Okay, so we are ignoring the support of the item set in the rule consequent. Okay, because of that the rule confidence might sometimes be misleading. Okay, one way to address this problem is by applying a metric called lift. So one way to address this problem, that is high confidence rule problems, okay, is by applying a metric called as lift. So one way to address this problem is by applying a metric called as lift. Lift is given by confidence of A implies B divided by support of B. Okay, so lift is given by this formula, confidence of the rule A implies B divided by support of B. For binary variables, lift is equal to another objective measure called as interest factor. So in the case of binary variable, the lift is called as interest factor. So let us see about this interest factor now. interest factor of a comma b is given by support of a comma b divided by support of a into support of b, which is equal to n into f of 1 divided by f of 1 plus into f of plus 1. Now, what is n over here? Total number of transaction. Here n is the total number of transaction. F11 is the frequency of occurrence of both A and B. F1 plus is the total support count of item A. And F plus 1 is the total support count of item B. So, this is the interest factor formula. N into f of 1 divided by f of 1 plus into f of plus 1. Now, the interest factor, this value, if it is equal to 1, then A and B are independent. If interest factor is greater than 1, then A and B are positively correlated. If interest factor is less than 1, then A and B are negatively correlated. So, based on the value of interest factor, we can tell that if A and B are independent, we can tell that if A and B are positively correlated, or if A and B are negatively correlated. Consider this example here. Okay, beverage preferences among a group of 1,000 people. Let us calculate the interest factor. Now, interest factor over here, the formula is given by n into F11, right, divided by support count of A, that is total support count f of 1 plus into f of plus 1. Okay, that is, in this example, interest factor of T coffee. Okay, interest factor of tea and coffee is given by n is 1000. Total number of transaction is 1000. So, 1000 into frequency of occurrence of both tea and coffee is 150, right? Frequency of occurrence of both tea and coffee is 150. So, 1000 into 150 divided by total support count of tea is 200, right? So, total support count of tea is 200. Total support, into total support count of coffee is 800, right? Total support count of coffee is 800. So, now if you simplify this, okay, cancel all zeros. You will get 15 by 16, right? You will get 15 by 16, which is equal to 0.9375. Okay, which is equal to 0.9375. Now, this is 0.9375. is less than 1, correct? It is slightly less than 1. So, we can tell that it is slight negative correlation between tea drinkers and coffee drinkers. Okay, because it is slightly less than 1, we can say that there is slight negative correlation between tea and coffee drinkers. So, this is how we calculate the interest factor. Okay. Now, let us see what are the limitations of interest factor. Association between the pair of words depends on number of document that contains both the words. Now let us see this example of finding the association between the pair of words. Okay, so in text mining, it is reasonable to assume that the association between the pair of words depends on the number of documents that contain both words. For example, now, because of their strong association, we can expect the words data and mining to appear together more frequently than the words compiler and mining, right? So, if you have a collection of computer science article, okay, the words data and mining would appear more frequently together than the words compiler and mining. Yes or no? So, because of their strong association, we expect the words data and mining to appear more often than the words compiler and mining in a collection of computer science articles. Okay, now let us look at the contingency table for the pair of words P, Q and R, S. So this is the contingency table for the pair of words P, Q and R, S. Okay, this entry over here suggests that the occurrence of both words P and Q. Okay, here this entry indicates that both P and Q does not occur. Okay, so and this entry suggests that frequency of occurrence of just an item Q but P does not occur. Okay, and this one indicates that occurrence of just an item P and where Q does not occur. Okay, same way this table, okay, of frequency of occurrence of words R and S. Now this is F11, right? Frequency of occurrence of both the P and Q. Okay, this is F00, where P and Q, both P dash and Q dash means it does not occur. So this is F00, right? Now this is F01, right? This is F01. Okay, frequency of where P does not occur and Q occurs. So it is F01. This is F10. Okay, so this is N. This is F plus 1. F of plus 0, this is F of 1 plus P occurs. This is F of 0 plus. Okay, same way this table. Okay, now interest factor for P, Q is given by interest factor for the word pair P, Q. Let us calculate the interest factor for P, Q. We know the formula. It is N into F11 divided by F of plus 1 into F of 1 plus. Okay, so frequency of occurrence of the word P, Q is given by N is 1000 here, 1000 into F of 1 is 880. Okay, divided by F of plus 1 is 930, right? F of plus 1 is 930. 930 into F of 1 plus is also 930. So this value is equal to 1.02. 1.02. Okay, now let us calculate the frequency of occurrence of the words R, S. Now let us consider this contingency table and calculate the interest factor for the word pair R, S. So interest factor for R, S is equal to n into n is 1000 f of 1 that is 20, right? So 20 divided by f of 1 plus, okay, that is 70 into f of plus 1 that is also 70, right? So this value you will get 4.08. 4.08. Okay. Now here if you see that although the words P and Q are more frequent than the words R and S. Okay, because the support count or the frequency of occurrence of P and Q is 880. But the word support count of word pair R, S is 20. Okay, even though the support count of P, Q is greater than the support count of the word pair R, S, but if we calculate the interest factor for P, Q is 1.02, which is less than the interest factor for the word pair R, S. So, although P and Q appear together 88% of the document, okay, their interest factor is almost equal to 1. Okay. On the other hand, R and S seldom appear. That is, they just occur 20%. Okay. Their interest factor is higher. So this is one drawback of interest factor. Okay. Here in this example, although the frequency or support count of the word pair P, Q is 880. Correct? Support count of the word pair P, Q is 880. Okay, and the support count of the word pair R, S is 20. Okay, but here if you see the interest factor for the pair R, S is 4.08, which is greater than the interest factor for the word pair P, Q. So this is one drawback of interest factor. Okay, so this was the example showing the limitations of interest factor. Okay, so this was an example of frequency of occurrence of the word pair P, Q and R, S. So this was the drawback of interest factor, that is association between the pair of words depends on the association between the pair of words in text mining. Okay, so next we have one more objective measure, that is correlation analysis. So it is used for analyzing relationship between the pair of variables. Okay, for continuous variables, correlation is defined by Pearson's correlation coefficient, which is given by correlation of x, y is equal to covariance of x, y divided by standard deviation of x into standard deviation of y. For binary variables, correlation can be measured using the D coefficient, which is defined as phi. Here represents the correlation analysis. Okay, it is a symbol representing correlation analysis, which is given by f of 1 into f of 0 minus f of 1 into f of 10 divided by square root of f of 1 plus, f of plus 1, f of 0 plus and f of plus 0. Okay, so this is the formula to calculate the correlation analysis. The value of correlation ranges from -1, that means it is perfect negative correlation, to +1, which means it is perfect positive correlation. If the variables are statistically independent, then phi is equal to 0. So if the two variables are independent, then correlation analysis is equal to 0. Limitations of correlation analysis. It gives equal importance to co-presence and co-absence of items. So it gives equal importance to both presence and absence of items. This is the limitation of correlation analysis. Another limitation is that it does not remain invariant when there are proportional changes to sample size. So the meaning of this sentence is that the value of that correlation analysis varies, okay, as the sample size increases. So when the sample size changes, the value of this correlation analysis also will change. Okay, so it does not remain invariant when there are proportional changes to sample size. Let us understand the limitation of correlation analysis with the help of this example. So consider this formula here for correlation analysis. Using this formula, I will calculate the correlation analysis for the word pair P, Q and for the word pair R, S. So let us begin. Now the correlation analysis, that is 5 of P, Q, 5 of P, Q is equal to f of 1 into f of 0. I'll write the formula again, otherwise it will be confusing here. F of 1 into f of 0, right, minus f of 1 into 10, f of 1 into f of 10 divided by square root of f of 1 plus into f of plus 1 into f of 0 plus into f of plus 0. Okay. So correlation analysis for P, Q. So here f of 1 is 880, correct? So 880 into f of 0 is 20, correct? So it is 880 into 20. Please forgive my bad handwriting over here. Okay. F of 1, which is 930, right? Sorry, f of 1 is 50. Sorry. F of 1. Okay, P does not occur, only Q occurs. So it is f of 1. It is 50. Into f of 10. Okay, this is f of 10. P occurs, Q does not occur. So this is f of 10, which is 50. Divided by square root of f of 1 plus, okay, that is 930, into f of plus 1, which is again 930, into f of 0 plus, which is 70, into f of plus 0, which is again 70. So this, if you solve, you will get the answer 0.232. Okay, you will get the answer as 0.232. Okay, so this is the answer that you get if you solve this formula. Now similarly, if I calculate the phi of r comma s, okay, so you should calculate phi of r comma s on your own. So phi of r comma s, if I calculate similarly, okay, based on this formula, if I apply to this and if I calculate phi of r comma s, I will get again 0.232. Okay, I will get same answer, that is 0.232. Okay, so here we can see that the phi coefficients of both p comma q and r comma s of the word pair p comma q and r comma s is 0.232. Okay, this is because phi coefficient gives equal importance to both co-presence and co-absence. Okay, so it is here the phi coefficient, it is more suitable for analyzing symmetric binary variables. Okay, now why it is more suitable for analyzing symmetric binary variables is that because their both presence and absence are given equal importance. So where the both presence and absence are given equal importance, okay, in such situations you can apply phi coefficient, because phi coefficient gives equal importance to both co-presence and co-absence of items in a transaction. So this was the limitation of correlation analysis. Next objective measure is IS measure. Now this is proposed for handling asymmetric binary variables. So the IS measure of a comma b is given by this particular formula, okay, and which is equal to f of 1 1 divided by square root of f of 1 plus into f of plus 1. Okay, so IS measure for the word pair a comma b is given by this formula, that is equal to f of 1 1 divided by square root of f of 1 plus into f of plus 1. So the IS measure for the word pair p comma q is given by 0.946, okay, which is equal to, by applying that formula, this formula if you apply, f of 1 1 divided by f of 1 plus into f of plus 1. Okay, so applying that formula, we get the IS measure for p comma q is equal to f of 1 1 is 880, right? So 880 divided by square root of f of 1 plus is 930 into f of plus 1 is also 930. If you solve this equation now, you will get this answer. Okay. Similarly, we can calculate the IS measure for r comma s using the same formula, which is equal to f of 1 that is 20 divided by square root of f of 1 plus that is 70 into f of plus 1 which is also 70. Okay, now solving this equation you will get this answer. So here if you see the IS measure for the word pair P, Q is given by 0.946 and the IS measure for the word pair R, S is given by the given as 0.286, right? Hence IS measure shows that the association between P, Q is stronger than R, S in contrast to correlation and interest factor. Okay, so if you use IS measure, it shows that P, Q correlation association is stronger than R, S. So it shows that P, Q is positively related than R, S. That is, the frequency of occurrence of the word pair data and mining, which is represented by P, Q, is greater than the frequency of occurrence of the words compiler mining, which is represented by R, S. So the IS measure over here solves the problem which could not be solved by 5 and interest factor. Next, limitations of IS measure. The IS value for the pair of independent item sets A, B is given as follows. So, for the pair of independent item sets, the IS measure is given by this formula, square root of S of A into S of B. Okay, the value of the measure can be quite large even for uncorrelated or negative correlated patterns. So, for independent items A and B, the value of the IS measure can be very large. Okay, for uncorrelated and negative correlated patterns. So, this is the limitations of IS measure. Next topic, alternative objective interestingness measure. These measures can be divided into two categories, symmetric and asymmetric measure. A measure M, so M is a representing measure, is symmetric if M of A implies B is equal to M of B implies A. So, measure M is symmetric if measure of A implies B is equal to measure of B implies A. Symmetric measures are used for evaluating item sets, while asymmetric measures are more suitable for analyzing association rules. Okay, so let us see the alternative measures. So these are the various other measures. Okay, objective measures, and they are formulas. Okay, so there is phi coefficient, Godman-Kruskal's measure, odds measure, Yule's Y, Q, Yule's Y, kappa measure, mutual information, J measure, Gini index, support, confidence, Laplace, conviction, interest, cosine, and various other measures. So these are the various other alternative measures. Okay, objective measures. So, and these are the formulas. Just go through all these measures. Okay. Now, comparing different measures. Now, how we can compare the different measures? Okay, here if you see this table, there are 10 examples in this table. So, if for two items A, B, consider there are two items A and consider there are two items A and B. Okay, so here F11 means occurrence of both A and B. F10 represents occurrence of item A only. F of 0, 1 indicates occurrence of item B only. F of 0, 0 indicates frequency that both occurrence A and B does not occur. Okay, so these are the 10 examples. Here they have given the ranking in this contingency table. Can you see that there are 10 examples here, E1 to E10, and these are the symbols representing the various measures. Okay, so these are the symbols representing the various measures. Okay, Gini index, support. Okay, now if you see over here, they are telling that for example 10, Gini index has a ranking 10 and interest has a ranking 1. Okay, that is here it is telling that interest is the most interesting measure because it has a ranking 1, for example 10. Okay, and Gini index is the least interesting measure, for example 10, since it has a ranking 10. So 1 means it is the most interesting, 10 means it is least interesting. So for this example 10, interest is most interesting measure and Gini index is the least interesting measure because the ranking is 10. So this is the shows the different rankings of the interesting measure for each of these examples. Okay, next topic, properties of objective measure. The first property, inversion property. Okay, so look at this transaction over here. So these are the vectors representing 10 representing over here only 10 transactions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So like that you can have n number of transaction. So each transaction represents is represented by this vector. So here 1 means for transaction 1 item set occurs. Okay, and here also for the 10th transaction item set item A occurs. So 1 indicates that item occurs for that transaction and 0 indicates that particular item does not occur in that transaction. So the bits 1 indicate occurrence and the 0 indicate that particular item does not occur. Okay, so these are the bit vectors. Here now if you see, vector C and E are inversions of vector A. So this is vector C and this is vector E, right? So if you see, these two vectors are inversions of this vector A. So vector A is the inverse of vector C and E. Okay, and again if you see that the vectors B and F, okay, the vectors B and F are inversions of this vector D. Okay, so vector D is the inversions of vector B and F. So this is the inversion property. So let us see the definition of the inversion property. An objective measure M is invariant under the inversion property if its value remains the same when exchanging the frequency counts F11 with F00 and F10 with F01. So this is the definition. Objective measure M is invariant under the inversion property if the values remains the same when you exchange the frequency count F11 with F00 and F10 with F01. Next property of objective measure is null additive property. So the null additive property says that the process of adding unrelated data to a given data set is known as null addition operation. So if you are adding unrelated data to the data set, then it is called as null addition operation. Let us look at this example now. An objective measure M is invariant under a null addition property if it is not affected by adding f of 0, 0, while all other frequency in the contingency table remains the same. See here, all other entries in the all other frequencies in the contingency table remains the same. Only entry that is changing is f of 0, 0. So here we say that an objective measure is invariant if under the null addition property if it is not affected by adding f of 0, 0, while all other frequency in the contingency table remains the same. That is, whenever you are adding unrelated data to a given data set, then only f of 0, 0 will change, right? F of 0, 1, 1, f of 0, 1, f of 1, 0 will not change. That is null addition operation. So I'll tell the example, that time you will understand it better. See here, suppose we are interested in analyzing the relationship between the pair of words data and mining. So if a collection of articles about ice fishing is added to the data set, now I have a collection of records, okay, where I find the relationship between the pair of words data and mining. Now I add a collection of articles about ice fishing to that particular data set. Should the association between data and mining be affected? What do you say? Will the association between the pair of words data and mining be affected by adding articles of ice fishing? No, right? If you add articles of ice fishing, in that article you will not have any words of data and mining. So adding the articles of ice fishing, that is adding the unrelated data set, okay, data to a given data set. Adding the unrelated data to a given data set does not affect this association between data and mining. Okay, that is about the null additive property. So see here, the process of adding unrelated data to a given data set is known as null addition operation. An objective measure M is invariant under the null addition property if it is not affected by adding f of 0, 0, that is unrelated items, while all other frequencies in the contingency table remains the same. Okay, so that was about null additive property. Next property of objective measure is scaling property. Now see this two contingency table which shows the grade gender example here. Okay, for female and male, grade is high and low. Now this is a table taken during the different time period here. Now suppose if let us assume that this was the contingency table showing the grade gender example in 1968. Where this was the contingency table showing the grade gender example in 2004. Now if you see that, if you see just to see this female data, okay, if you see the female data, can you see the number of females have doubled, right? So it is into 2. If you see the male data, can you see the frequency of males have increased 10 times, correct? Here it is 3, here it is 30. Here it is 4, here it is 40. So the frequency of the male count has increased 10 times. Okay. Now, here if you see the ratio, of males, if you see the ratio, here it is 3:4, correct? So if you see the male ratio over here, male ratio for high and low grades, it is 3:4. Here if you see the male ratio for high and low grades, it is again 30:40. Okay, ratio of male who got high grades is to ratio of male who got low grades, which is also equal to 3:4, right? Which is also equal to 3:4. So the ratio is same in both the table. Okay, though this table, the second contingency table, has scaled 2 times and 10 times, the ratio of male students who got high grades is to the male students who got low grades is 3:4 in both the tables. Okay, so the relationship between gender and grade should not change just because of the sample size. So even though the sample size has scaled, the relationship between the gender and grade should not change. So we need a measure that is invariant to scaling of rows and columns. So the measures should be invariant with the scaling of rows and columns. Let us see the definition of scaling property. An objective measure is invariant under the row-column scaling operation if m of t is equal to m of t dash, where t is the contingency table with the frequency counts f of 11, f of 10, f of 01 and f of 00, and t dash is the contingency table with the scaled frequency counts, that is k1 into k3 into f of 11, k2 k3 into f of 10, k1 k4 into f of 01 and k2 k4 into f of 00, where k1, k2, k3 and k4 are positive constants. So in other words, if I have to explain it in simple, so if the objective measure does not change even when the contingency table has scaled, okay, then that objective measure satisfies the scaling property. So the objective measure which does not change even when the contingency table has scaled, then that objective measure satisfies the scaling property. So this was the definition about scaling property. Next, see this slide here. Here they are showing the different measures that have different properties. So these are the different measures which satisfies whether it satisfies or not the different properties. You can see the inversion property, null addition and scaling property. Here if you see, the phi coefficient satisfies the inversion property but does not satisfy the null addition and scaling property. Okay. Next, if you see odds ratio, it satisfies inversion property and scaling property, but it does not satisfy the null additive property. Cohen's objective measure satisfies the inversion property but does not satisfy the null addition and scaling property. Okay, if you see the Jacob here, Jacob objective measure, it does not satisfy inversion property but it satisfies the null addition property, and also it does not satisfy the scaling property. If you see interest measure here, it does not satisfy any of the properties. It does not satisfy inversion, null additive nor scaling properties. Similarly, all confident and support measure does not satisfy any of the properties. Right? So this was the different measures, whether they do satisfy or do not satisfy the different properties. Let us continue. The last topic is Simpson's paradox. Okay. Now, what is the Simpson's paradox? Let us see. We must take caution when interpreting the association between variables. Observed relationship in data may be influenced by the presence of other confounding factors, that is, hidden variables. So the observed relationship in the data may be influenced by the hidden variables. Hidden variables may cause the observed relationship to disappear or reverse in direction. This phenomenon is known as Simpson's paradox. Okay, so Simpson's paradox is nothing but, okay, it is a phenomenon in which the hidden variables will have some effect in the observed relationship in data. So observed relationship in data will be affected by the hidden variables. Okay, that phenomenon is known as Simpson's paradox. So let us see the Simpson's paradox with an example. Now if you see here, now this is a two-way contingency table, correct? Here you're showing in the table you're showing the customers who buy HDTV and customers who buy exercise machine. Okay, so you're telling here 99 number of customers buy both HDTV and exercise machine. So here 81 is the support count of customers who just buy HDTV but do not buy exercise machine. Similarly, 54 is the support count of customers who do not buy HDTV but just buy exercise machine. And finally, 66 customers do not buy both. Okay, and this is the total support count. Here if you see, suppose we have this rule, if a customer buys HDTV, then he will buy exercise machine. Okay, now over here if you see, confidence of this rule is equal to 99 divided by 180. Okay, that is customers who buy both divided by support count of HDTV, that is 180. So customers who buy both are 99 divided by support count of HDTV. Okay, that is here confidence. We know the formula for confidence, right? Support count of both HDTV, I will write it as H, and exercise machine, I will write it as E, divided by support of the left hand side, correct, antecedent, that is support of HDTV. Support of HDTV is 180. So it is support count 99 divided by 180, which is equal to 55%. Next we have one more rule, okay, which tells that if a customer does not purchase HDTV, then he will purchase exercise machine. Okay, so HDTV is equal to no implies exercise machine is equal to yes. So this rule tells that if a customer does not purchase HDTV, then he will buy exercise machine. Again, calculating the confidence of this rule, support count of both HDTV is equal to no, exercise machine is equal to yes is 54, correct? Support count of HDTV is equal to no, exercise machine is equal to yes is equal to 54, divided by total support count of HDTV is equal to no is 120, right? Total support count of HDTV is equal to no is 120. So 54 divided by 120 is equal to 45%. So this was the confidence generated from this rule. If a customer does not buy HDTV, then he will buy exercise machine. Now if you see the confidence of both these rules, you can see that customers who buy HDTV are more likely to buy exercise machine, right? Because its confidence is high. Okay, so if a customer buys HDTV, then he will buy exercise machine. That rule has higher confidence than if a customer do not buy HDTV, then he will buy exercise machine. So from these two confidence, you can see that customers who buy HDTV are more likely to buy exercise machine. So this was calculating the confidence using a two-way contingency table. Next, let us see over here. This is a three-way contingency table. Okay. So this is a three-way contingency table. Here, along with buy HDTV, buy exercise machine, we have added one more factor here, that is customer group. Okay, so it is three-way. Customer group, buy HDTV, buy exercise machine. Here the customer group may be college students and it might be working adults. Okay, so let us examine the same two rules over here. That is, if a customer buys HDTV, then he will buy exercise machine. And one more rule is that if a customer does not buy HDTV, then he will buy exercise machine. Now, for college students, if we calculate, okay, for considering only college students, if a customer purchases HDTV, then he will buy exercise machine. So, support of both HDTV and exercise machine for college students. Okay, for college students, it is given by 1 divided by total support count of HDTV is equal to S. For college students is 10. Right? So it is 1 divided by 10, which is equal to 10%. Next, let us calculate the confidence of the rule. HDTV is equal to no implies exercise machine is equal to yes for college students. So college students HDTV is equal to no is given by 4. Okay. HDTV is equal to no, exercise machine is equal to yes. HDTV is equal to no, exercise machine is equal to yes is 4. Divided by total support count of HDTV is equal to no is 34. Correct? Total support count of HDTV is equal to no is 34. So 4 divided by 34, we get 11.8%. Okay, so this was about the college students. Next, let us calculate for working adults. So for working adults, the confidence of the rule that if a customer buys HDTV, then he will buy exercise machine is equal to, so confidence of both HDTV is equal to yes and exercise machine is equal to yes is given by 98, right? Divided by total support count of HDTV is equal to yes. So total support count of HDTV is equal to yes is 170. Okay, which is equal to 98 divided by 170, which is equal to 57.7%. Next, let us calculate the confidence of the rule. HDTV is equal to no implies exercise machine is equal to yes for working adults. Okay, that is, if a customer do not buy HDTV, then he will buy exercise machine. So the confidence of this rule is, so HDTV is equal to no, exercise machine is equal to yes. So for working adults, the value or the frequency is 50. Right? HDTV is equal to no, exercise machine is equal to yes, it is 50. Total support count of HDTV is equal to no is given by 86. Right? So here you get 58.1%. Now, if you see both these confidence, okay, it reveals that confidence of customers who do not buy HDTV but buys exercise machine is greater than the confidence of customers who buy both HDTV and exercise machine, right? So a deeper analysis here reveals that the sales of these items depends on whether a customer is a college student or whether he is a working adult. So here if you see, the support count in this table sums up to the support count of the first table, right? So here if you see, the support count 1 plus 98, if you add, you will get 99, right? So yes and yes, that is HDTV is equal to yes, exercise machine is equal to 99. That is summing up the support count of both college students and working adult. Similarly, HTTV is equal to no, exercise machine is equal to yes. If you add 4 plus 50, you get 54. So here what they are telling is the support count of the second table sums up to the support count of the first table. The rules suggest that for each group, customers who do not buy HTTV are more likely to buy exercise machine. Now the factor over here, now if you consider in more detail, that is the customers who are college students and customers who are working adults, okay, you can see that the customer who do not buy HTTV are more likely to buy exercise machine, correct, since the confidence is higher over here, which contradicts the previous conclusion when two group of users were summed up, correct? When two group of users were summed up, you saw that customers who bought HTTV also buy exercise machine, their confidence was higher compared to the customers who do not buy HTTV but buy exercise machine. So this is a contradict, okay? So here the sales over here of HTTV and exercise machine is being affected by the hidden variable, that is a group of customer, whether a customer is a college student or whether he is a working adult. So this was an example of Simpson's paradox. Here I want to tell you all this row sum. So this is a row sum of college, see this table, here this row sum indicates this is a sum of HTV is equal to yes. So this is the total frequency count of HTV is equal to yes. Okay, this is the total frequency count of HTV is equal to no. Okay, now this is the column sum over here. This is the total frequency count of exercise machine is equal to yes, and this was the total frequency count of exercise machine is equal to no. So these are the row sum and this is the column sum. Okay, so that was about Simpson's paradox. So we are ending with the third module. This is the end of third module. If there is any doubts, you can ask me in Google Classroom. So thank you.